Hi! In the previous video, I went through the comparison test, which shows how absolute convergence is being used and proven. In this video, we'll show more types of comparison tests, namely the root test and the ratio test. So let's begin first with the root test. So we are given a series and we let alpha equals to limit superior of the nth root of an, and you want an to be positive, so you need to put the modular. You want the terms, you can only input the positive numbers always, so you want to put the absolute value for the terms an. And if the limit superior, the lim sup, is less than 1, then we know that the series converges absolutely. And if a is greater than 1, alpha is greater than 1, then the series diverges. If it equals to 1, then the test gives us no information. And we shall prove it first before using it. So, if it's less than 1, then by the definition of lim sup, we can choose a beta such that there exists an integer so that it leads to this inequality being whole because of the characterization property. And you can really watch my video on lim sup in earlier videos to understand that. So because there'll be infinitely many terms smaller than this beta, so you reach this conclusion. And then you just take the nth power, and then you see that a to the power n, the absolute values are dominated by this beta to the power n terms. And since beta is between 0 to 1, the summation will be this geometric series which will converge. And as a result, this means that an converges by the comparison test. And you can really see how the comparison test is being used to help us prove a lot of different type of tests. And so really the comparison test is really the one that is very, very useful. But because of this root and ratio test later that we are going through, it shows how you can just straight away apply it instead of always thinking what to bound. And then if alpha is larger than 1, then the sequence an will approach alpha from some subsequence will approach alpha. And because of that, you can just take to the power nk, and since an is greater than 1 for infinitely many values of n, this means that for the series to converge, the terms an must approach 0, which can't hold true if alpha is greater than 1. So how you think about it is this terms ank, the modulus, approaches alpha to the power nk. And alpha is greater than 1, so this term will always get infinitely bigger. So an can never approach 0, means the series can't converge. And so we've proven the second part. And if alpha equals to 1, you can consider these two series which have both alpha equals to 1, but 1 over n diverges and 1 over n squared converge. And so we are done with the proving of the root test. So I hope it's clear how we're going to use it. And in most times, people just consider the limit, but you should be really looking at the lim sup, because then you can use this characterization property. And the next part before we move on to examples will be just to show you what is the ratio test. And really the ratio test is saying that the series converges if the lim sup, which always exists, then you just take the ratio of the next term an plus 1 divided by an, and you show that the lim sup is less than 1. and it diverges if this ratio is greater than 1, which means that the lim sup will never be less than 1 also. And if condition A holds, meaning the lim sup is less than 1, then you can find a beta less than 1 such that the ratio will always be less than beta. And in particular, this means that an plus 1 will be less than beta and an plus 2, now you have to expand this, will be beta an plus 1 less than beta squared an, and then you so on. So retermings the terms, it will be an will be less than a capital N times beta to the power minus n times beta to the power of little n for all n larger or equals to capital N. And then if it just follows directly that since beta is less than 1, this part converges, means an converge. And so if an plus 1 is larger than an, then you can see that an will never approach 0, because it will just keep increasing positively. And so part B holds. And of course, if the limit is 1, then it implies nothing about the convergence, and you can just use the same series example to show why. And so let's just look at these examples to show how we apply the root test and ratio tests. And these examples also give us a chance to introduce why a root test is actually better than a ratio test. And that's because if we consider the series half plus 1/3 plus half squared, the limit inferior will be 1/3 divided by half to the power n, which equals to 0. Because you just need to take the nth term divided by the previous one. And the limit inferior of the nth root is 1 over 1 square root 3. You can just verify yourself. But that's not important, because what you really want to know is the lim sup. And so the lim sup of the nth root is 1 over square root 2. And the lim sup of the ratio is actually plus infinity. And the root test shows that because this is less than 1, it converges. But the ratio test cannot be applied since it's infinite. And then this is also true for this following series, where the terms are just jumbled up. And we already know that this is actually a geometric series, so it will converge. But if you just take a look, the lim sup is 2 and the lim inf is half. So the lim sup doesn't say anything about convergence. And will actually be saying that it is false. So the ratio test may be used because it's easier to apply. However, the root test has a wider scope. Or more precisely, you can say that whenever the root test shows convergence, the ratio test will show. Whenever the ratio test shows convergence, the root test will show as well. And whenever the root test is inconclusive, then the ratio test is inconclusive. And so let's see why this is true. And basically, you just want to show that the lim sup of the nth root is always less than or equals to the lim sup of the ratio. And so if the ratio is less than 1, then of course this will be less than 1. And if this is already greater than 1, then of course this has to be greater than 1. So let's just say the ratio lim sup is alpha. If alpha is plus infinity, we are done. So if alpha is finite, then we can choose a beta larger than alpha. And as a result, by the characterization property, there will exist an integer such that Cn plus 1 over Cn will be less than beta for all n greater than or equals to capital N. And then you just bring over, and then you just expand out all the way to the pth term, which then you can rename the terms, like how we proved the ratio test earlier. And now you just take the nth root of it, and then you realize you have a beta here and this chunk over there, which is a constant. I mean, beta is the constant, and then you got this chunk, and you know that this part approaches 1 when you take the limit, and so the lim sup of this will be less than beta, and so it follows that it's true. And so since 18 is true for every beta, then the lim sup must be less than alpha. And we're done with proving the inequality. So really practice using the textbook by Bertley and Schobert or Rudin on using the root test and the ratio test, and then you'll just be familiarized with these two tests. That's all for this video. Thank you for listening, and feel free to like, share, and subscribe, and I'll see you in the next video. Bye.